Good. All right.
Someone really likes this order was very good. I gotta do this a lot. Yeah. Yeah. Oh, great. Please sign in. Very important.
Do you have audio? Is the question.
Got nature's place right now.
Yeah, sorry, I didn't feel like.
1, 2.
I don't know what it is, but see, like. Come on over there too. Sorry.
You got a couple weeks. Started writing.
Alright, started writing. Started over again.
That's how these things go.
Yeah, dude, I'm like harder. Like, I think if we get like if we get
Okay, I'm fine.
yeah, so
I don't have that. I'm happy to supply a solution. I am soliciting this.
Yeah, please.
If you think that my time is there, this is
Wait, what was the third?
Well, the code started.
Yeah, come on.
right now we do have the stack upsized
Really polished, yeah.
went there,
Have places.
changed my name. Same subject, but different wording.
Yeah. How related is that to?
There are a lot of you that did
You were going to affect the size, since we have small calculus, very exactly not standard, not standard. If you're not able to do that, then I wouldn't be able to do that. So we get active as passive, active as targeting, passive as
I don't.
because there's also targeting actions really help them. It provides such a size and whatnot.
I don't.
No number of words. That's not a bad thing.
I think all students are.
It's more so.
And discipline every single one. Yeah. Sign in.
That's how we get reimbursed.
We're still waiting.
Ever anybody feel like they don't think
No. Oh yeah. Cool.
Wait. Does everybody else?
All right.
What's your?
Or you could read.
Number 12.
Right on time.
Yeah.
But I just don't want us pushing every business break.
Even if you're not eating this, sign in. Sign in twice. Sign in 3 times. Chicago.
Are you advocating for free drive?
That is not what I am. I am advocating pizza.
It's illegal better.
University of Missouri.
Thanks for sending them this. Yeah,
Major. Yeah.
I mean, nothing, I'm gonna.
Hey, what's up, everybody? Welcome to GMods. I'm gonna get going, and probably more people are going to walk in, but we have an exciting docket today. Yay. Yay! I'm sorry, I'm a little bit out of it right now. Yeah, this is gonna be great. So the talk I prepared today is on the topic of standardizing synthetic biology, and I captioned that with "Should we even bother?" For the reason that I think it's an interesting question, and I'm really interested in you guys' input as well. So feel free to stop me and ask questions in the middle. And then I have a slide at the end also soliciting people's opinions on some of these topics. But I got started kind of with this quote that I found when I was researching that I think is somewhat relevant, but also just kind of amusing. This is from Tom Knight, one of the forefathers of the field. A biologist goes into a lab, studies a system, and finds it far more complex than anyone suspected. Spends a lot of time exploring the complexity of writing a paper. An engineer goes to the lab, makes the same finding, and responds, "How can I get rid of this?" And I think that's kind of right. A lot of the talk of doing standardization of synthetic biology kind of owes back to this idea of engineering biology, that biology is inherently an engineering discipline, and that we could take, for instance, a bunch of screws that are different sizes, and we could just make them all one-size screws, that the same screwdriver fits all of them. And this was the idea that kind of came from the early days of synthetic biology. We need to make a toggle switch or a repressolator using parts that we can exactly hardwire together in order. And the idea behind a lot of this was that part standardization would allow better sharing of materials, better protocol standardization between research groups, we could have this universal registry of parts that work together and play nicely together. You could get experimental reproducibility, which has been in the news, of course, recently in a lot of different academic fields. And then finally, this sort of just, I think, embodiment of what I have is the Lego dream, which I have not actually trademarked here. But this idea that if you get the parts in the right order, they're going to function in the right way together every time. Now we know a little bit better that that's probably a little bit disingenuous. Rob Carlson says there are very few molecular operations you can understand in the way a wrench or a screwdriver or a transistor. And I like Christine Agapikis as well. There's a lot of biology that gets in the way of the engineering, and that's been one of the constraints on the field recently as well. So I am talking about part standardization, but I'm also going to talk about other types of standardization at the end of this talk. But we're going to start with one of the initial goals of standardization in synthetic biology, which is parts. And when I use the term part, I'm specifically referring to things like promoters, RBSs, specific coding sequences of genes, terminators, all the different aspects that can make up a genetic circuit. And the original idea behind this was the idea of biobricks, where you literally have Lego bricks that each of these things represent, and you can string them together in an orderly fashion to design a genetic circuit. This is from early work from the ND lab, where they designed this whole fabrication strategy of biobricks, where you take the part that you care about, it's got some nonsense alphanumeric characterization behind it, where VBA F2620 is something, and E024 is something else. And they have restriction sites that are complementary, so that if you want to put these two things together, you can just do a quick digest of one part, a quick digest on the other part, and then the overhangs will be complementary and you can stick them together. And then the idea is, you piece these two things together, and you can make, as you have at the bottom here, an inverter or something that smells like a banana, or buoyancy of cells, where all you have to do is take your regulated promoter and stick it in front of the gene that you care about, for instance. There's some challenges associated with this. So the original design goal of these biobricks had a lot of rules. One, of course, is that if you're using restriction cloning, you can't have restriction sites in your construct of interest. So those were the sites that were banned, E4R1, XFAL, SP1, PSP1.I. You cannot have that in any of the parts that you care about. And they also recommend not having any of the 5 sites below that either, which was one problem with this whole design. So there's the idea of part standardization really took off in the early 2000s, and I think right now we can mostly look at it as a failed experiment, because just as a show of hands, who here has ever done biobricks cloning or assembly? Who here still does biobricks cloning and assembly? Yeah, I've done it before. There's a lot of reasons why people don't do this. I think the first one is that restriction cloning blows. We can all agree on that. It's not good times. The second is this idea with incompatible sites in your genes. So I did the math behind this, so there's like a 90% chance I did it wrong, but the probability of having any one of those 10 6-pair restriction sites in a 1,000 base pair gene is 92%. The probability of having more than, or 3 or more of them is almost 50%. So if you're taking some gene out of an arbitrary organism of interest and you want to stick it in your genetic circuit, odds are very, very high that you're going to have to recode it in some way to block the illegal restriction sites. And if you're going to do 3 cycles of site-directed mutagenesis, then you might as well just do a Gibson assembly anyway, because like restriction cloning sucks. Additionally, DNA synthesis wasn't or isn't that cheap. I think we can still argue about this, but if you wanted to take a gene of interest back then, it wasn't as feasible to just go to Twist and say, hey, can you make me this 1,000 base pair gene that's been recoded so that it doesn't have the illegal restriction sites? Now it might be a little bit more feasible to do it, but it's still not accessible for a lot of research groups. Additionally, there were some constraints on how they actually designed these restriction sites. So it produced the ligation between the 2 sites when you're sticking 2 things together creates what's known as a scar, and that scar is unfortunately out of frame, so you can't make fusion proteins, which is kind of silly. It only allows for transcriptional coupling between parts and not necessarily translational coupling between parts. There's ways that people have been getting around this by using alternative approaches like bagel bricks, but that wasn't the original design of the biobricks. And then finally, I think an important thing is that there's really no practical way to enforce this. Originally, when there were only so many parts and biobricks said, these are all the screws that the field is going to use, then it's a lot easier to say you have to use our design rules. But once we started having a much bigger explosion in our knowledge sets of synthetic biology, creating new promoters and RDSs and so on, it became much more difficult for people to actually be forced to obey these things. Christina Smolke, about a couple of years, this is an article, an opinion piece from 2009, essentially talking about the iGEM and Diobricks Foundation, talked about why these things never caught on, and there's a couple things that I think resonate a lot with what I've been mentioning. One is that a lot of labs didn't want to do it. If you're an established lab, you've already got a whole bunch of parts, and you have no interest in adapting them for the rules that this foundation is imposing on you. The difficulty in coupling types of parts together due to the stars. And then finally, and what's important here is that the quality of the parts in the registry was not generally good. And I think we've all probably heard these rumors, is that if you get something out of the iGEM registry of parts, like, maybe it's right, hopefully it's right, but it's not always right. And there hasn't been great validation on a lot of the pieces that are in the registry, even to this day. So iGEM requires obedience to these standards. I know that the iGEMers in the crowd here are like, oh God, we had to deal with all of this. Anytime you make a part as part of an iGEM project, you're supposed to ship it to the registry, you're supposed to document it, you're supposed to show its use in some sort of functional circuit, and it has to be Diobricks compatible, which means that you have to have the right restriction sites on it, you have to make sure that you don't have any illegal restriction sites anywhere in part of your genes, and then this allows the next iGEM team a couple of years later to just take their part and directly plug it into their system. That's not necessarily great though, and leads to some challenges. So this was the worst review I found on the registry of parts in a 5-minute search, but there's a lot of things like this, is people will submit parts to the registry, and then other people will comment like Yelp, like, no, this doesn't actually work, you lied, you screwed up your experiment, who knows? This seems like advertising their own part on someone else's part, which I think is amusing. Theoretically, it should be possible to sequence the entire iGEM registry. It's got about 20,000 parts. That might be off. I actually think it's more than that now. So it shouldn't be like ridiculously expensive to do all of that, but no one really has a vested interest in doing it right now. And another constraining factor, I think, for this is that anything that's made as part of an iGEM project is officially in the public domain, so it's not patentable. And there's some indication that if you're an iGEM team trying to make something, trying to start a company with it, you have no real reason to participate in their little game in trying to make everything publicly available. That's not necessarily related to part standardization, but I think it's an important constraint.
Double check. So this is $1 million of Sanger sequencing?
Yeah.
That looks like you could probably do like one run of Illumina.
Sure, yeah. But you'd have to get all of the parts into a form that would be compatible with Illumina sequencing, so I don't know how.
20,000 mini preps.
Yeah, exactly. The other thing I think that's important is this idea of part standardization. I mentioned this beforehand. How disingenuous is this? The idea that they're actually Legos. And there's like a gajillion papers out there now kind of calling into question our knowledge of how well parts actually function independently of each other. I just picked 2 random ones here. But this is a really recent paper at the Arkin Lab that's basically talking about translational or sequence constraints on translational functionality, and shows that basically we don't have the slightest idea. There's a ton of design rules that weren't previously known in E. coli. This is another paper that Jim Collins and Richard Murray worked on, where they're showing basically that you can take a genetic circuit that functions in one direction, and then if you just flip it on the plasmid in the other direction, everything is broken. This is an actually recent article in Scientific American where Vijay Pandey, who's better well known, I think, in the tech community, but publishes this whole idea of can we take this dream of Legos synthetic biology and put it together? And he's arguing that CAR-T therapies should be able to be directly controlled just by knowing promoters and coding sequences and everything. And we should be able to design how it will function. This, mind you, is from like 2 weeks ago, and the entire reaction from the synthetic biology community has been like, dude, no, you don't know what you're talking about. So the question, and this is kind of the end of the part standardization bit, are things different now? Is there a possibility of us actually being able to, as a field, come together to make the stream a reality? You know, costs for DNA synthesis and sequencing are now much lower. So you have options like high throughput sequencing as well. There's probably a growing community enthusiasm for openness. One example that I pointed to here, I don't know if Kirsten's going to mention the newsreel, is just recently there's been a push for this open MTA agreement that was published in Nature Biotech piece earlier this year, and that's been really spearheading a lot of the ideas of really being able to share parts and plasmids between labs. And I think we have now gotten to the Socratic idea that we really don't know what's going on, but maybe having all the pieces in the same context as each other would maybe make it a little bit easier to start uncovering some of those design rules rather than confidently asserting that we know everything. So that's part standardization. There's other approaches that people have been doing for synthetic biology standardization. This first one right here was from an NAR paper out of the Kiesling lab in 2016, and it's this idea of kind of an orthogonal registry that they're calling JBay ICE out of JBay, where it's a combination of both a part database, but also tools used for implementing genetic circuits and so on, so that you know that this engineering and cloning approach can be used to design a circuit in exactly this way. And as far as I can tell, this hasn't actually taken on outside of JBay, but it's an idea out there, and they're also promoting how open source everything is with this. So all the software that's being developed as part of this pipeline will be freely accessible. There's been a lot of work in this similar vein in the UK in recent years. So Richard Kidney has been one of the pioneers of these ideas. SynBIS, I don't know exactly, has been promoting this idea of a data acquisition standard in synthetic biology, where you can both make a part database, where in this case they have some promoter, they characterize all of the experiments that have been done on this part in controlled situations with controlled experiments, rather than ones that iGEM teams are reporting. You can see all the uses of this, all the experiments that have been done with it, and then the way that the data is being organized, both collated real data and metadata. Other ideas that people have been thinking about in the field: experimental standardization, increased accessibility to parts and designs is an important one. Publication standards and design standards. I'm going to touch briefly on a few of these. So the first one is standardizing experiments. This has been a real goal for iGEM and BioBricks for a while as well, is how can we actually maintain the fact that an experiment that's run in one lab is exactly similar to an experiment that's run in a different lab. They're enforcing this also in the iGEM teams now these days by having them do these inter-lab experiments. This is a very simple bit of data collected from this early paper, John Cumbers, by the way, on this paper, okay, where they're characterizing promoter strength across different labs. That's what each one of those bullets is representing, and using this sort of artificial measurement that they call relative promoter units or polymerase equivalents, you can get relatively good agreement between the labs as long as you do the proper normalization that they laid forth in their paper using an in vivo reference standard. There's also been efforts more recently in trying to expand this beyond just bulk fluorescence assays. So this is the MIEO, which you can actually find online as a standard. It's like publicly available on a Google Drive, so you can just sort of edit it if you want to. Kind of concerning. But they have established specific criteria for developing, in this case, flow cytometry experiments in synthetic biology. They identify something like 35 different parameters that seem to be the most important, and specify what the values of them should be so that you can get reproducible results from one lab to another. And they do a very high scale sensitivity analysis on all of these different parameters. That's what's being represented on the left there across different research groups. There's also been a push for design standardization and publication. The synthetic biology open language has been a real push in that direction. So if you're drawing a gene circuit in your paper, you should use the glyphs that they tell you and don't represent a promoter with like a stop sign. If you do that, you have other problems. I don't know. Just to indicate how late I was working on this presentation last night, that's a paper from BioArchive that came out last night showing how you can definitely didn't make this slide last night. Showing that you can actually use SBAL now they're trying to expand the glyphs for multicellular systems. And this, I think, has been catching on a lot. ACS Synthetic Biology in particular has really been pushing people that submitted that journal to be following the glyph notation so that you don't have a whole bunch of different designs out there. Sharing parts is another important aspect of this. AdGene has been immensely useful for this. There are issues associated with AdGene, the MTAs that have to be agreed upon between the two universities that are sharing the parts, as well as the costs associated. So SynBioHub is one example of the standards-enabled repository for synthetic biology, where the idea is that you can upload your designs and then they can be shared easily and interface well with things like Benchling and the ISO. And I'm not entirely sure where this is situated right now and how popular it's gotten. So if anyone has used it, let me know. I'm wrapping up right here. Like I mentioned, I wanted to, and this is a discussion for anyone, so I have a slide on that at the end here, but just a couple of few assorted thoughts. It seems like part standardization, I don't know if it's seen it today and it's never going to come back, and I'm willing for other people to try to sell me otherwise, but it seems like it's going to be immensely difficult, knowing the number of labs that are participating in synthetic biology these days, to really ever be able to get it to work. I mean, case in point, even if you're just using like Golden Gate standard assembly in one lab, it's hard to get a lot of people on the same page with that. It might arguably be inimical to other trends in SynBio. I'd be interested to hear what people that are interested in DIY bio, for instance, how that is impacting the ability of, for instance, a community lab, if they have to adhere to the same standards as everyone else, and how you can enforce that. There's also, I think, a question on, we're getting to the realm of being able to make a lot of DNA really quickly, and to some extent, if you just make all the primers and make those things available to the community, a bunch of short pieces of DNA, every possible RBS, the synthesis for that is absolutely now scalable. You could make every possible RBS and make that publicly available. Is that an option that's not maybe part standardization, but really opens up the field of possibilities that the community can benefit from? And the last thing I have here is that we should all start using methyls. As someone that has only done experiments with fluorescence in grad school and reports everything in our units, I'm sorry, but you should all do it. So yeah, last slide I have here is, what do you think? Is standardizing synthetic biology worth it? I'd love to hear any thoughts on it. Yeah, it's actually.
So with this idea of buying every possible primer,
Yeah.
I'm confused with what the point of that is.
I mean more like synthesizing it. Not that you're like buying it necessarily, but saying that like that DNA now exists in some central repository that you can continuously amplify or something using PCR, so that if you wanted to go to Twist and say, I want to order this particular part, they can just ship it to you. They don't have to synthesize it every time.
But how long do those sorts of things last? Like a 20 nucleotide piece of DNA, even in their freezers, how long? Like,
I mean, a double-stranded DNA. Like,
yeah.
What?
But how often have you, like, what is the oldest primer you've used, like, for example? So are these things going to be still quality after 5 years? Is it cheap? Like, what is the benefit of actually synthesizing those, or rather just having them synthesize it when you need it?
Yeah.
I don't know. I don't.
It seems like
Like, I don't know what the benefit is.
compared to just like synthesizing it new.
Yeah, from IDT, you can buy a primer, get it next day.
Yeah, I mean, chemical synthesis of DNA is it's inefficient from an atom economy perspective. It's probably worse for the environment overall than doing a PCR. And if all of the templates exist, then why are we still making them? I guess is the question. I don't know. Again, I'll talk through all these ideas. Yeah.
So standardizing biology is absolutely worth it.
Okay. Thank you, Isaac.
Yes, definitely worth it. You've done a really good job of laying out the flaws with the current approaches. And what I would say is that there are initiatives underway, particularly through the BioBricks Foundation, to take those lessons learned Like, okay, well, the first assembly standard, the fiber standard, wasn't super easy to use and didn't really work really well on like just arbitrary pieces of DNA you pull because they might have the restrictions in them. And it was difficult to get everyone on the standard because there were just this like small pool initially, and everyone already had their own parts and didn't want to spend the time and money to convert. So that's all true, but that's what the Free Genes Project is for. So Firebricks Foundation has secured the funding to purchase and make freely available to everyone 15,000 synthetic genes. And so the plan is to basically remake every useful part that from like the last 20 years of synthetic biology and put it on the same standard, and then make it freely available to everyone. And then everyone uses it because it's free.
Is it gonna happen though?
Yeah.
Okay.
It's gonna happen. Yeah, I mean the goal is like not just like to have a central repository of this, but like everyone can have their own Free Genes repo local to them and able to store it once we figure out the paper-based storage stuff. It's gonna happen.
I hope so. Seems like a good thing. Yeah.
Two questions. The first is with respect to what's being standardized.
Yeah.
Do you see that in what you've researched as more in the standardization of how genes are assembled, such as on the backbone, or do you see it more as how they're characterized and measured? And then I'll do the second one.
Yeah. I would argue probably the first one is more important because when you take it, like no one is going to, and maybe this is the flaw with the field, is that you can go in and say, all right, this promoter in somebody else's experiment worked like this, but no one really does the same basal experiment with this promoter in their own system, right? So like I can say that I'm going to take this promoter that the fancy flow cytometry using all the controls said was a 30% strength promoter of consensus, but I'm not going to believe that it's going to be 30% of consensus in my own hands because I'm not going to be doing that same experiment. So I think it's more important for things like design where we say that we are always going to put insulate transcriptional units, and we are always going to make sure that we don't have scars between our promoter and RBS or whatever. And these are just examples. Other people can disagree with me.
That makes sense. And then for the second part, did you get any sense for whether the standardization push is primarily in the prokaryotic context or if it's also in other types of model systems?
It seems like all of the examples that I can find, there are a few examples of use standardization, but push has been bacterial. And that's honestly probably just because that's where synthetic biology is the best at and we know the most about. But you're right, it's kind of a shame that we yeah, no, I think it's right. In some cases, I think bacterial transcription and eukaryotic transcription are so radically different that you need a completely different way of standardizing what a promoter looks like, right? Just the mechanisms are radically similar.
Yeah, there are plant Moclo toolkits and mammalian Moclo toolkits that are different from the bacterial ones. And then like people are trying to make like standard landing pads in different genomes you can stick stuff in. So just
Yes. Working on that right now.
Cool. Any other thoughts? Anyone? So yes, standardization. Yeah, I think so. Yes.
So another thing about the composability problem,
Yeah.
like them not quite working the way you expect them to when you put them all together. I feel like maybe part of that is like a problem with how the experiment is designed, like because a lot of the times there are like multiple different ways you can achieve the same output function with like slightly different architectures or using different parts, and it might behoove the field to move towards a like, okay, this is the output we want. These are like 5 different architectures we can use to achieve it, and these are like 3 different variations on those architectures using slightly different parts that are predicted to work. Now we're going to make it really cheap to assemble and make all of those and screen them, and then we'll find the ones that work.
Yeah, I think that's important, and a lot of the push recently for hard characterization has been, can we make the experiment as minimal as possible, right? So even something like this, I don't think I put like the Anderson promoter promoter library on here. This is a really good example. It's like Chris Anderson characterized a whole bunch of promoters and said, if you make this mutation to this residue, then it's going to take, or to this nucleotide, it's going to take a 30% hit in its activity. That's done in an in vivo experiment on some copy number plasmid. So I think there are ways that we're going to do these part characterizations. Vincent Noiro has an editorial, for instance, saying that like cell-free is a much better way of characterizing that. I would go even further and saying like purely in vitro experiments where you are literally just like doing transcription from the promoter and measuring the RNA output is the most minimal experiment that you could be doing because there's just so many interactions there that you have to characterize.
So given that there are so many interactions though, is it super valuable to have that very minimal characterization as opposed to like a characterization of this promoter plus this gene of interest that I want to do?
I mean, I think that right now we are believing the number from the Anderson promoter library is saying that it's going to be a 30% hit, and that's not true any more than this one would be. But at least this, you can have some sort of direct functional output that doesn't have all of the other numbers wrapped up into it. You can see it the other way too, though, is that if you care about in vivo expression, then you want your experiment to be done in vivo, and you can see that too. They don't measure in that experiment. They don't measure the consensus bacterial promoter because they did all the experiments on a high copy vector, and the consensus promoter in the high copy vector isn't expressible in cells because it's toxic.
Well, then at that point, why would you want to standardize anyway? Because characterization in this context is going to be different than everybody else's experiments. And so why don't you just have like a standard set of design rules with how cheap DNA is going to be? The experiment that you propose to set up different variations of things, that doesn't really use a standard set of things, just a standard set of ideas of what promoters or elements would be there. So why spend all this time and energy on the like part characterization rather than just come up with better sets of design strategies in different contexts?
Yeah, I agree. I think that's where the field, personally, I think that's where the field should move. But I mean, that was the question, right?
Right.
Is it worth doing this? I don't know.
I mean, maybe it's not like one or the other. It's not like either we have to perfectly characterize these things or there's no point in doing it, but more like, all right, let's characterize these things enough that we can constrain the design space down and into like a manageable number of variants that we can build and test.
Fair, yeah.
It's also a question of who's going to do the characterization. Right? I don't want to spend my PhD looking at 900,000 promoter variants.
Make it an undergrad class.
You
Build a
have
bio
that,
lab.
the S-ball designer cartoon. There's the character.
Yeah.
That's what you do.
Sometimes it feels like my PhD is doing 900,000 cool. Any other insight? Anything? Cool. All right, thanks, guys.
Thanks for the great talk, Adam. Hi, everybody. For those of you who don't know me, my name is Kirsten. I'm a second-year PhD student in the Lux Lab, and today I'll be giving you Speaking of standardization, 2018 January happened a couple weeks ago, late October, and the results are in. Over 300 international teams competed. Majority of them were collegiate labs, although there are two community labs, which I thought was interesting. And then I highlighted some of the medals and also the finalists of each track. And of course, Northwestern IGEM team also was able to participate and compete at the Jamboree. And then I have a picture of our team presenting their project benefits. I also wanted to kind of highlight the winner of the undergrad track, which is from UPD, which is a university in Spain. And their project is titled Bacteria. And the project basically aims to kind of broaden access to synthetic biology by public by eliminating any of the barriers, such as like required expertise knowledge and expensive lab equipment. So the whole idea is that to come up with the device that can automate the process of printing genetic circuits in bacteria. And they were able to design this by using different digital microfluidic system and software applications to basically come up with a printer that you can just operate like a desktop printer that'll print genetic circuits. That was really cool. So if you're interested in learning more, I encourage you to check out their website. So Moderna Biotech's IPO valuation came out to be almost $7 billion, which is the largest biotech IPO on record. For those of you who are not familiar, Moderna is a biotech company developing medicines based on hospital strands of mRNA. And the idea is that these mRNA treatments are designed to trigger cells to make proteins that prevent or fight diseases. The company has a lot of big investors like Merck and Vertex Pharmaceuticals. They also have a lot of revenues from their collaboration partners and research grants. However, their operating costs are really high. It has been high for a couple of years, last couple of years, almost over $300 million. And this cost is expected to go up even more because only half of their drug candidates are now entering their early clinical trials. However, the company is still doing really well. They don't have any debt as of the late September of this year. So yeah, we'll see how the company does with this IPO. Another kind of shocking news, Illumina has agreed to purchase Pacific Bioscience for $1.2 billion, kind of to cement its ownership of cutting-edge genetic research. And this article talks about how the deal will be the largest that Illumina has ever done in its 20-year history. To kind of go over like what the difference is between the other companies. The Illumina sequencing, we all know that they use a sequencing by synthesis, and this technique made possible below $1,000 on human genome sequencing, but they have shortcomings because they do short read synthesis. It's really difficult to sequence a DNA that has been structurally rearranged or has a lot of repeats because it makes it difficult to assemble at the end. That's where the PECVAR comes in with their smart sequencing, which stands for single molecule real-time sequencing. For this technology, they utilizes a natural ability to replicate DNA, and this technique is available to read a very long stretch of DNA. However, it's a lot more expensive compared to the Illumina technique. It costs about $12,000, I believe, to sequence the genome. So the idea is that Illumina can help bring down this cost of the long read technology. Some of the papers, so the Baker Lab, they published 2 papers in the last month. The first one being the fluorescence activated beta barrel. This is really actually exciting because there has been a lot of examples of polyhelical structures that have been designed de novo using simple models, but there has been not much success with beta barrels. In this paper specifically, they built beta barrel backbone models with cavity shape that matched fluorogenic compound. And then they tested this designs in vivo and also in vitro, and found that the proteins were able to activate fluorescence. This has potential in designing ligand-binding proteins, which is really exciting. And then this paper, the bottom one, came out more recent. They designed filaments. If you are like me and like looking at different microscope images of proteins, you should check this paper out. They have a lot of different geometries of pretty pictures of filaments. We all knew this, but yes, CRISPR can do much more than just gene editing. This paper came out in Nature titled Transcriptional Reporting by CRISPR Spacer Acquisition from RNA. Here, instead of gene editing, they use CRISPR to capture and convert intracellular RNAs into DNA, and that enables DNA-based storage of transcriptional information. To do this specifically, they utilize RT-Cas1 and Cas2 proteins. Just quickly, Cas1 and Cas2 are proteins that can integrate new spacers, ahead of all spacers within the CRISPR array. So that can provide a temporal memory of events. And specifically, RT-Cas1 can integrate not only DNA but also RNA into CRISPR array. So yeah, in this method, they can basically record according to RNA abundance, incorporate that RNAs in CRISPR arrays, and And then I guess they call the technique recourse-seq, and then they highlight that it's better than RNA-seq in that you can kind of report a transient and continuous molecular events on RNA-seq. And so more CRISPR-Cas9 research papers. The first paper talks about recent discovery of phage-derived anti-CRISPR proteins that can naturally inhibit type 2 CRISPR systems. But they talk about how we don't have mechanisms to control this anti-CRISPR proteins. So they came up with a method to kind of trigger this anti-CRISPR proteins with external light stimulus. And then the paper in the bottom is another application of CRISPR other than gene editing, which is a live cell imaging. They talk about how they kind of enhance the traditional way of using CRISPR for live cell imaging by making this very stable RNA aptamer structure. They call aptamers or something. Basically, they have all this like 8 aptamers in a row with a 3-way junction, and they show that it really enhances the stability of RNA, and then you can also amplify the signal that way, so it enhances the live cell imaging efficiency. Mammalian synthetic biology also had a pretty exciting papers out this month. The first paper from the Wise Lab in Nature Chem Bio. They basically came up with a platform for small molecule-based regulation of modified RNA and also self-replicating RNA. Specifically for modified RNA, they control its expression by fusing RNA binding proteins to destabilization domains that are targeted to protease unless stabilized by a small molecule. And they talk about how the system can potentially be used for therapeutic applications such as inducible cancer immunotherapy. And then the second paper point out the limitation of RNA-encoded multi-layer networks in mammalian symbio because there are only a handful of orthogonal regulatory devices, and they kind of attempt to expand this available tool set by using protein-protein interaction-based device through engineering also RNA binding proteins. Oh, and then also Cell-Free Symbio had some of the publications in Synthetic Biology Journal. The first one highlighted here, they used cell-free system to implement a genetic oscillator, and they used this in, as you pointed out, Anna pointed out in protein, they used microfluidic flow reactors to do this, and they basically, and then utilize the system. They were able to optimize kinetic model with experimental data they pulled out from cell-free experiments and use that to kind of quantify some key regulatory model parameters. And then the second paper is from the Jewett Lab, talking about how they developed a in vitro regulated synthesis assembly and translation system, which they call ISET, in cell-free extracts for ribosome construction. So this paper basically highlights how power of cell-free symbio for doing high throughput screening and optimization. I also want to highlight some of the really interesting articles that came out last month. This one came out in Nature. This is about synthetic cells, and it's a really comprehensive summary of how the field is going and where the field is heading. Some of the interesting facts I pulled out, obviously the synthetic cell technology has really benefited from recent advances in microfluidic technologies. Recently there have been a group formed called Building a Synthetic Cell. NSF also announced its first program on synthetic cell funding about $10 million. And I thought this was interesting. The article highlights that, or they claim that the bottom of synthetic biologists can create first fully artificial cells within a decade, which I think is a little optimistic. Legit for microfluidic thinking. Another kind of comprehensive summary article about gene drives. It really has a lot of information on pros and cons and ongoing debate about gene drives. Again, some of the interesting parts is highlights how CRISPR-Cas9 really enabled gene drives to be reality. By 2016, gene drives have been created in yeast for flies and also mosquitoes to eradicate mosquito-borne illnesses. But also there's obviously concerns associated with it. We don't know what ecological role those species will play. So we don't know what seagrass will affect ecology in the future. So yeah, it's a really good review. So if you're interested, I recommend checking it out. Yeah, so now you can apparently buy design on microbes to replace fertilizer from Pivot Bio, which is a startup biotech in California. So yeah, they announced its commercial launch of the first and only nitrogen-producing microbial treatment for U.S. corn farmers. This is not to be a replacement, a full replacement for fertilizer, but rather to help reduce the amount of fertilizer we use, because we know that traditional fertilizers are a huge contributor to greenhouse gases. So this effort is to kind of reduce that environmental negative impact of fertilizers. Yeah, and EcoBioverse is now launching into another kind of level of using cells as factories. Traditionally, they've been using bacterial and yeast cells to make biomaterials like leather and stuff like that, but now they're launching a new program, BioX4, where they're basically accepting orders for engineered luminal cells from mice to hamsters to humans. So, yeah, that's also. And this, Adam mentioned this at the end of his presentation, but yeah, this article came out and how they're now trying to develop an open MTA system. Just to kind of go over, MTA is basically a stands for Material Transfer Agreement, and it's a construct that governs the transfers of different research materials between collaborators and organizations. But traditional MTA kind of prevents two things, which is they don't allow redistribution of materials, and they also don't allow commercializing of these materials. And to kind of get around it, that they formed a group of people who construct an open MTA, which is basically the same thing as the traditional MTA, but without these two constraints. Yeah, and then a bunch of bioorganic papers, you should check it out. The first paper is actually a collaboration between the Lux Lab and Brugere Lab here. They developed a quantitative and systematic kind of computational approach to automatically detect RNA folding events from a large co-transcriptional data sets. And then the one below, they're using microfluidic droplets to kind of select for certain biosensors. And then the top, I guess, where you guys top right. So they use a engineered system to kind of sense and respond to fungal pathogen, which is the most common cause of candidemia. And to kind of wrap up, I wanted to highlight some of the upcoming CSB events. December 12th, we're going to have Jeff Tabor as a speaker, so everybody should come. And some of the other CSB upcoming talks, I'm sure there's going to be more information floating around. You guys are probably getting a lot of emails about them, but we're having these really big speakers coming, so look out for that. Also, it's never too late. We're still looking for speakers, so if you're interested in giving a talk, please contact us.
Or if there are people you know that
Or
would be
interested.
interested in doing it.
Yes, that also.
Right. Please,
Oh, yeah.
sign
Yeah,
in.
please sign in.
Sign in. I will let you have another piece of pizza if you sign in.